Okay, guys, so this video is going to be quite short. It's talking about an assignment you're going to have to do from the book. I'm going to get you started with just the general setup of it. I'll just share my screen here. So in the Zoom meeting yesterday, we talked about, oh boy, what happened here? Hang on. I think that's the one there. There we go. So in our Zoom meeting yesterday, we talked about how to do a titration, what a titration was, and we gave just to quickly show that um, lots of different types of calculations, and the idea that really a titration was a way to predict something you didn't know about, some kind of chemical maybe you were interested in, and so we really tend to focus on the concentration of an unknown chemical was the sort of the general gist of most of the questions. And then right near the end, Noah had asked a question about how do you know when you reach this equivalence point? Like, how do you know you're actually at that place where the moles of H plus equal the moles of OH minus? And so this is going to sort of show, or the assignment anyway, is going to show uh, what's sort of unique about a titration compared to many other experiments that we do in chemistry, and how precise the titration actually is, like that you actually do know with a great deal of certainty that you actually are at the equivalence point. So I want to just start by going through a question that we did a while back, and involved determining the pH when you mix like a strong acid and strong base together. So I'm gonna use pretty much the exact same question we did previously, and uh, let's say you mix um, 20 mils of 0.10 molar HCl with let's see, you had 10 mils of 0.10 molar NaOH. And so this is the kind of question where you had to choose between two formulas, whether you had excess hydronium or excess hydroxide. So the first thing I think we might want to do is find out the concentration of the hydronium and the concentration of hydroxide that we would be starting with. And so what we have here is for hydronium, it would have to come from the HCl. And so that is 0.10 molar. And then times it by a dilution factor of 20.0 mils over, we're writing 10, so 30 mils. And then for the hydroxide, it would be equal to, so right now this is 0.1 molar also, so 0.10 molar multiplied by a dilution factor of 10 milliliters to 30 milliliters. So if I work that out, my, let's see. So we have 0.1 times 1 divided by 3. So I'm getting 0.0333 molar. And the hydronium is similar, 0.1 times 2 divided by 3. And so this is 0.0666, and that repeats 2 molar. Okay, so obviously there's more hydronium here, so the overall solution should be acidic. But what we're kind of curious about is, or what I'm kind of trying to get you to think about is, do you think it's much different from what it started with, or is it pretty close? And so if we look at the pH of the HCl, and so this would be just basically on its own. So let's say you measured the pH of the pH, not pOH. You measured the pH of the HCl on its own before you even mixed it. Well, you would just take the negative log of the hydronium, which would be 0.10 molar. So right now you've got a pH of 1.00. And then you add, if you look at what you added basically half the volume of base that you had of the acid, and the concentrations are the same. So you're adding, a good chunk of base here. But would the pH be acidic, basic, or neutral? Well, if you subtract these numbers, you get 0.0333 molar, and that would equal the concentration of hydronium in excess. So that's what you have left over. So if you worked out the pH of the solution, and that's after you mixed it, then that would equal the negative log of the hydronium, which would be 0.033333. So it's a little harder to work on in your head. You can actually ballpark that number and see it's not much different actually. So negative log of 0.03333. And so we're getting a pH of 1.47. So that's really not much. That's less than half a pH unit difference between what you started with and what you got. So if you think about the amount of base, you added a fair bit here, but let's say you really ramped it up, and let's say that you did the exact same experiment. So we're just going to switch. So I'll start here. So same question, but instead of 10 mils of base, let's say you added 15 mils of base. And don't forget, like in order to neutralize this, if you have 0.1 molar acid, 0.1 molar base, and you have 20 mils of acid, well, then you're going to need 20 mils of base to neutralize everything. So I'm choosing a number a little bit smaller than that. And once again, I'm not going to worry too much about sig figs right now. It's more concepts here I want you to think about. So if you did 15 mils, then the concentration of the hydronium should still be in excess. But let's work out what we start with. So this would be equal to the concentration of the acid, which is 0.10 molar, multiplied by a dilution factor. Dilution factor of, so same question, 15 mils of base now. So 15 mils of base being added. Yeah. So you're getting closer and closer to that magic number of 20. So now, so the hydronium here, well, that would be still 20 mils of acid. But now the volume is 20 mils plus 15, so 35 mils. And the concentration of the hydroxides would be equal to 0.10 molar multiplied by, now it's, instead of being 10 mils, it's 15 mils we're adding, all over 35 mils. Okay, so let's use our calculators here. So 0.1 times 15 times 1 divided by 35 is equal to 0.04287. And then we go 0.1 times 2 divided by 3.5. And that equals I did that wrong. Let me just double check that. 0.1 times 2 divided by 3.5. 1.1 times 15 divided by 35. So that's that number. And then we do 0.1 times 20 divided by 35. So we're getting 0.0 0.0571. So once again, the hydronium is still in excess. So we are obviously in an acidic condition. So I go with that number minus 0.04287. So the hydronium in excess would be equal to 0.01427 molar. Okay, so what would the pH now be? pH here, we're going to negative log that number. And so I'm getting a pH of 1.845. So you can see here, you're getting a pH of 1.47. Now we're getting a value of 1.85. And basically you added almost half of what you added in the previous example. So this idea of adding an acid to a base, it does change the pH, but notice it doesn't change it very much. So I'm going to get assigned a question here from the homework, and it's a graphing question, so you're going to have to draw out the graph. And it really is a fundamental understanding of what a titration curve looks like. And so what you're going to be graphing is two axes. So one here would measure a volume of base, and on the other axis will be the pH. 1 to 7 and up to 14. And so you want this to be drawn with a ruler, and then the assignment's going to be handed in as one of your homework assignment questions. And I want you to really pay attention once again to the shape of this curve. So it's very unique. It's not something I think you would probably maybe have forethought or had thought it would look like this. So the question is on page 166, sorry. And you're given some data. And that data, you're going to graph it then. So you can draw it by freehand. You don't have to use a computer, but you're going to have pH on the y-axis and volume of base on the horizontal axis. And then you're going to plot the information given on page 166. There's two charts there. So you're going to graph those, and that's going to be a homework assignment. So make sure you do look over that. And let's see if you can answer questions. Page 166, question number 124. And you're going to do 124A. And that's the graphing part I was talking about. Just kind of explain to you there. I'll have the answer C. Actually, this is yeah. And B. Let's do B. See, and let's do D. Okay, so there's not a lot here, but I did want to just show you that when you mix acids and bases together, it's very unlikely you're going to get a neutral pH 7 result. Usually you have a bit more of one than the other. So I hope this helps a little bit. I think that's going to be, yeah, that's it. Okay, so I'm going to sign off from here. It's getting late for me.